Good morning, friends. So today we will study one quantum mechanical model. So this is like potential something called infinite square potential. So we will study one quantum state system, which is side is infinite square. So I will finish what is the implementation of this kind of simple model in physical world. So let us try out what is the four potential past. So this is can be given like this. So this is infinity, and let's say x equal to 0 and x equal to L. And this is 0, L square. So this is the mathematically you can write out this potential like this. So one more thing is I can say like this is the one-dimensional potential we will be studying here. And if you draw schematically, this potential will look like this. This does the carbon showing how this potential look like. So this is the one-dimensional potential here. So you can see this is the length is L. And now we have V equal to infinity here, and V equal to infinity here, and V equal to 0 here. So that means this potential well can be modeled by three regions. Here, there is 0 inside. That means particle cannot tunnel to this region and to this region. Only particle there is the probability of finding particle inside this region. Okay. So this is a typical model, simple model you study in this quantum mechanics. So what we have solve this kind of potential well using our equation of motion in quantum mechanics. This is called time dependent Schrodinger equation. Okay. So I will write down Schrodinger equation. So this is the differential equation which gives rise to dynamics of this quantum particle simply by this solution. This is the one-dimensional equation as I already told you. Now, one way to write down Schrodinger equation like this. Next, what we will do, we try to solve this Schrodinger equation in three different ways. First way, second, and third. As I mentioned, we don't need to find out the solution here and here because this potential is quite infinite. It's very high. Particle cannot go there. So we are only interested in this region where this particle can move free. But we will see this particle is not completely free in this region because with this boundary condition we will see later how the energy level will function. They are quantized. Okay. So simply for region 2, you can write down for region 2. This equation simply gives rise to let's say u of x equal to 0, as I mentioned here, and this is a way. So now this will be simplified as like this. So your u of x equal to 0, then you can write simply like this. So you can see this equation now simply looks like the second order differential equation. Okay. So now solution you can find out by solving auxiliary equation. For example, in this way. 2ab by x squared and then this is sine of. So this bracketed part is known as your auxiliary equation where identified is n equal to d by d. So this is standard solution, standard mathematical procedure how to operate solution of second order homogeneous differential equation. So now let's define something of another parameter x square equal to ab by x squared. Okay, then this equation reduces to equal for m square plus k square sine. Because the psi cannot be 0, that means the bracketed term will be 0, which you guys will take to plus minus I. So this is your m. The parameter will be defined explicitly. Now, what is the general solution? Then for this region 2, general solution. So this will be, as you know from our standard principle. So it can be like this: psi of x equal to a sin kx plus b cos kx. So as you can see, there are two parameters. This is a and b. So now if you want to find out this, then only you will get the opposite solution. So how to find out these two parameters? So we have already enough information in our table. What is that? That's boundary condition. This boundary condition. That means at this boundary x equal to 0, the function is 0. Similarly, at x equal to this. That means put x equal to 0 here, then you will get one boundary condition. Okay, something that's 0. Another boundary condition x equal to here, this will be 0. So these are the two boundary conditions. Okay, so now once you solve this boundary condition 1, what you will get? Get the value of constant b equal to 0. If you substitute this and then you solve this equation, you will find out easily b equal to 0. Similarly, from the second boundary condition, you can see we will find out the condition for k, which is nothing but n pi by n. So what is n? N is the positive integer. It starts from, let's say, for example, 1, 2, 3 up to 8. Okay, but the main part is this is integer, positive integer. So now, with this condition, what is our final solution will look like? This will be like now here psi of x equal to a sin n pi x by n equal to 1. Okay. So the interesting part is now you can write down for each n a different value function. Okay, so these are the larger steps of the next model, for example. Because for every n, if you are considering this, and the n is not technically fractional value. This is an integer value. That's why this is quantized. Okay, so this is the algorithm for each n. But now the most important part is, as I said, this particle is completely free here. That means the what is the kinetic energy? Free means there's only kinetic energy, but restricted kinetic. That means the wave vector is, as I mentioned here, is quantized. Because if you will take now not a continuous value, but rather a discrete value. N is your discrete value. Kinetic energy again quantized. So what is the interesting part? Because for a free particle we know the energy is continuous. It can take any value. But surprisingly, the particle is free here, but not completely free because there are boundaries. Okay, so due to this boundary effect, the kinetic energy is no longer continuous, but rather taking some discrete. That is why this simple and simple model that explains the quantization of energy in a squirrel. So what is this physical universe? Because using this simple model, one can study very realistically. For example, the confinement of proton and neutron inside the nucleus. So you can model the nuclear potential by using this infinite squirrel potential. Another example is like you can see there are you take the infinite chain of this potential, okay, in periodic fashion. Then this will correspond like nearly free electron model in solid. Okay, so this is having a very high physical levels. Not exactly you can see this is the exact model, but at least a prototypical model for different physical scenarios. Okay, so this is one I want to tell you about the classes. Okay, in the next one we'll see another. Thank you.